discuss concurrency control. Okay, and these are the chapter contents. First, we will see need of concurrency control, why we need the concurrent execution of the transaction. Then we will see lock-based protocol to implement this concurrency control mechanism in transaction management. Lock-based protocol is used. That is the basic protocol. We will see that. Then locking protocol we will see. Okay. Then in this chapter, you will basically discuss about these three things. First, we'll see what is the need of concurrency control. Already I have told you. Whenever the transactions, so suppose multiple transactions are there, T1, T2, T3, three transactions are there. Whenever these transaction and each transaction has number of instructions. When these transactions will be executed in serial manner, that means that is a serial schedule. First T1 will executed, then T3, suppose then T2, or first T1, then T2, then T3, then or first T2, then T3 or T1. All are known as your serial schedule. And serial schedule results in consistent state of the database. Okay. But what is the problem of serial schedule, or what is the problem when transactions get executed in serial manner? That means one transaction get executed completely, then other transaction get executed completely, then other transaction get executed completely. Okay, always the main advantage in serial schedule is your always it guarantee your consistent state of database. But what is the disadvantage of this? The main disadvantage of serial schedule, or main disadvantage when the transactions are executed in serial manner, is that time consuming or CPU utilization will be less. CPU performance will be less. Okay, to increase the CPU performance or to increase the CPU utilization, what we have to do? We need the concurrent execution of the transactions. That means, suppose each transaction consists of several instructions, and some of the instructions are IO bound, and some of the instructions are CPU bound. Whenever one transaction is executing its IO bound instruction, at that moment, other transactions should be assigned to the CPU to execute its CPU bound instruction, so that CPU will be busy all the time. And when CPU will be busy all the time, CPU utilization will increase and performance of the system will increase. Okay, that is the main aim of CPU. We increase the CPU utilization, and that is the main of concurrent execution of transactions. Okay, then the need already I have discussed for avoiding longer waiting time of transaction. If transactions involve multiple steps, some involves IO activities and other involves CPU activities. In a computer system, CPU and IO operations can be done in parallel. Therefore, IO activities can be done in parallel with CPU activities. So that when IO activities done parallelly with CPU activities, the processor and disk utilization increases. And what is a schedule? Already I have told you in previous class. Order in which instructions of transactions get executed. Okay. Then this is all about the need of concurrency control or need of concurrent execution of transaction of a schedule. Now we'll see what are the problems whenever the transactions are concurrently executed. Suppose T1, T2 transactions are there. Suppose here I1, I2, I3, I4. Four instructions are there. Here also I1, I2, I3, I4. Four instructions are there. Concurrent execution means suppose T1, I1 of T1 get executed, then I1 of T1 get sorry I2 of T1 get executed, then suppose I1 of T2 get executed, then I2 of T2 get executed. That means first two instruction of T1 get executed, then first two instruction of T2 get executed, then one instruction of T1 get executed, then one instruction of T2 get executed. This is your concurrent execution. And when such kind of concurrent execution happens, at that moment, but data inconsistency arises. Okay, that we will see here. There are several kind of problems generally arises due to concurrent execution of the transaction. First one is a lost update problem. These are the five basic problems arises when concurrent execution of transactions happens. First one is a lost update problem. This is otherwise known as a write-write conflict. I will tell you in details later on. Then temporary update or data read problem. This is otherwise known as a write-read conflict. Okay. Then your incorrect summary problem we will see. Then unrepeatable read problem or read-write conflict we will see. Then phantom tuple problem. These are the five basic problems which are arises generally due to the concurrent execution of transactions. Okay, now we'll see first one, that is a lost update problem or write conflict. When such kind of conflict arises, I will tell you. Suppose this is a schedule and it consists of two transactions. Okay, this is a schedule S1. It consists of transaction T1 and T2. First, instruction 1 read A of transaction T1 get executed. Then second instruction of T1 get executed. Then first instruction of T2 get executed. Second instruction of T2 get executed. Then third instruction of T3 get executed. And this is the sequence order of in which the various instruction of T1 and T2 get executed. That means this first executed, then this, then this, then this, then this, then this instruction get executed, then this instruction, then this, then this. In this order, the various instruction of various transactions get executed. But in this case, what happens? Suppose in this case, initially, transaction T1 is a transfer of $100 or 100 rupees from account A to account B. And what is transaction T2? Transaction T2 is your transfer of 20% of account A, 20% from account A. Okay, transaction T2 is transfer of 20% from account A. Okay, if T1 and T2 executed serially, then what happens? Okay, suppose initial value of A is equal to 100 and initial value of B is equal to suppose 100. This is your initial value of A and B. Then suppose a transaction T1 and T2 executed serially. Then what will be the database state? We will see. Suppose first T1 get executed. When T1 will get executed, then read A value is your 100. Then A is equal to A minus 100. That means A value will be 0 here. Now here it will read A value as 100. Here A is equal to A minus 100 means 0. Write A means it will write the value of 0 in your the buffer. These changes happens in local memory and these changes happens in buffer. Then read B means what is the value of B? 100. Then B is equal to B plus 100 means it will make the B value to 200. Okay, that means what will be the value of A and B after completion of T1? A value is equal to your 0, B value will be your 200. Okay, then after completion of T2 transaction, then what will be the value of A? Now read A value is equal to how much? 0. Then temporary 2.20% of 0 is equal to 0. That means A value will be your 0. That's true. Okay. Now, if you will concurrently execute this transaction, okay, if we will do the concurrency execution, that means first two instruction, then this instruction will be executed, then what will be the value of A and B after completion of T1 and T2 transaction, we will see. Okay, suppose initial value of A is equal to 100, initial value of B is equal to 100. Okay, then T1 get executed, then first two instruction of T1, it will read A value is equal to 100, then A is equal to A minus 100, then A is equal to 0. Then A value is equal to here 100 now, but it has not updated till now. Then T2 get executed. When T2 will get executed, read A. What is the value of A? In buffer, A value is equal to 100. That's why A will be here 100. Then temporary is equal to 20% of A. That means temp is equal to 20. 20% of 100 is equal to 20. Then A is equal to A minus 10, and A is equal to 80. Okay. Then write A. Write A means how much? It has updated here. That means 100 minus it has 0. This is in local memory it has changed, but it has not changed in the buffer. That's why when this T2 transaction reads the data item, it will reads the A value as 100. Okay. Now write A means what value T1 will write in the buffer? A value will be here 0. Then write A means this write, it will write the local memory value to the buffer. That means A value will be here 80. 80 will be written here. A value in the buffer. That means in buffer, A value will be here 80. Then read B. B value is equal to 100 and B is equal to B plus 100 means B is equal to 200. That means after execution of T1 and T2, the A and B value will be A value is equal to your 80, B value is equal to your 200. But it should be A value should be your 0 and B value should be your 200, because whenever the transactions get executed in serial manner, they generally what gives you the consistent result. That means A value should be 0 after execution of these two transactions. But as these two transactions get executed in concurrent manner, A value becomes 80 here. Then why such value we get? Why this inconsistent value we get here? Due to this write-write conflict. Okay, this is known as lost update problem. That means why this problem arises whenever two write operation on same data items in two different transactions occurs at that moment. If here no read operation is there in this transaction, and here one write operation is there, after that another write operation of another transaction is there on same data items, then such kind of problem arises. That means this second transaction write operation will update the value of first write operation. Here the first write operation has written 0, but when this write has written, it has updated it to 80. That means this is a lost update problem. That means the value of first write operation transaction, the write operation of transaction T1 got lost due to the write operation of transaction T2. Okay, this is a write-write operation, write-write conflict. Okay, this problem occurs when two transactions that access the same database item have their operations interleaved in a way that makes the value of some database item incorrect. Okay, if there is any two write operation of two transactions, that means here one write operation is there of T1, where one write operation of T2 is there. Between that, there is no read operation. That means in between no read operation is there. The second write operation overwrites the first write, hence comprises loss of first operation. Okay, the second write operation overrides the first write operation value. That's why the loss of first updation happens here. This is your lost update problem, WW conflict. Okay, such kind of transaction is such kind of instruction should not be present in any transactions. Two transactions which are concurrently executing. This will create your problem, lost update problem. Now we'll see temporary update or data read problem, or this is otherwise known as your write read conflict. What is this? Suppose T1 and T2 two transactions are there, then you can do first you execute T1 and T2 in serial manner, then you get the data items A value and B value. Similarly, you execute in the manner how the instructions get executed. First this, then this, then this instruction, this instruction. In this way, you will see what will be the state of A and B. When you will see in concurrent execution, you will find the inconsistent state of A and B. Okay, then why such inconsistent state arises? This is known as temporary update or data read problem. That means here, suppose initial value of A is equal to suppose 100. Okay, and initial value of B is equal to 100. If serial execute, then what will be the result? We will see here. Okay, first T1 get executed. Read A, that means A value will be your 100. Then A is equal to A minus 100 and A is equal to 0. Write A means 0. It will update in buffer A value to be 0. Okay, then suppose here we will take A value to be your 200 and B value to be 100. Okay, A value is your 200, then your A value will be here 100, A minus 100, then here A value will be your 100. It will write the value of A to be 100. Then read B, B value will, that means it will create A to be your 100 in your buffer. Then your read B, B value is your 100, then it will update B is equal to B plus 100. That means B value will be your 200. That means after execution of transaction T1, A value will be your 100 and B value will be your 200. Then after execution of T2, what will be the value of A and B? We will see. Read A, that means it has updated the value of A in the buffer. That means it will read the value of A as 100. It will not read the value of A as 200. That means it will read A value as 100. Then temporary 20% of A, that is your 20. Then A is equal to A minus 10, that means 100 minus 20 is equal to 80. Then write A 80. Then write A means it will write here 80. That means A value will be here 80. Okay. Transaction T2 tells that A value will be your 80. That means after completion of T1 and T2, what will be the value of A and B? A value will be your 80. That is the last update by transaction T2. B value will be your 200. Okay. Suppose now we will see, suppose concurrent execution of T1 and T2 happens. Okay, if concurrently we will execute these two transactions, what will be the value? Okay, suppose initially it will read A, that means 200, A is equal to A minus 100, that means 100, write A means 100. Then it has a read value as 100, then it will be 20, then it will be 80, A is equal to A minus 10, then write A means 80. That means A value will be your 80 and B value will be your 200. Okay, then what problem arises here? We will see here. Suppose when transaction T1 is getting executed at that moment, suppose here failure happens. That means if we execute T1 and T2 in serial manner, A and B value will be 80 and 200 respectively. Similarly, if we execute T1 and T2 in concurrent manner, then also we will get A and B value to be 80 and 200. Then what problem arises? When suppose the T1 has executed this much of instruction and T2 has executed this much of instruction. After that, before executing this instruction, suppose failure happens. When failure happens, then rollback will happen. I have already told you atomicity property. When a transaction is not executed completely, then it will be rolled back. When transaction T1 get rolled back, then the A value will be how much? 100. The A value will be a 200 because complete state of the database will be rolled back. A value will be 200. But whatever updation has been done by T2, taking the A value as 100, and this will not be rolled back because transaction T2 was completely executed. That's why this is a problem. And this problem is known as temporary update or dirty read problem. Okay. Whenever in one transaction T1 write operation of one data item is there, and in T2 transaction one read operation on the same data item is there, in between no commit statement is there. That means suppose one transaction is reading a data item which is written by another previously another transaction without execution of commit statement, then if the first transaction get failure and it will roll back its value, then T2 get affected. That means whatever data items has been read by T2, that is a wrong data or dirty data. Okay, this is your known as temporary update or dirty read problem. This problem occurs when one transaction updates a database item. Here T1 transaction updates the database item, right A, and then the transaction fails due to some reason. Here suppose the transaction fails due to some reason, the updated item is assessed by another transaction. That means the updated data items, it has updated to 100. Initial value of A was 200, it has updated to 100. That has been read by transaction T2 and all the operations are executed based on that A value 100. Okay, by another transaction before it is changed back to its original value. That means it has not changed back to original value. Before that it has updated, T2 transaction has updated the value of A. That's why it is creating problem. Okay, reading of uncommitted data is called dirty read operation. That means whenever one transaction is reading any uncommitted data items value, that is known as your dirty read problem. Okay, and such kind of problem generally arises inconsistency of data items. Okay, or inconsistency of database. This is your temporary update or dirty read problem. Now we see incorrect summary problem. Suppose two transactions T1 and T2 are there. Here T1 is there, T2 is there, and one transaction is doing some operations. Okay, it is transferring 100 rupees from account A to account B. And another transaction is suppose calculating the aggregate or summary function. Suppose it is calculating the summary sum of both transaction A, what content of transaction A and content of transaction B. At that moment, what happens if some of the updation task of T1 has executed? After that, the summary will be get executed or summary instructions get executed. Then it will what create the incorrect summary. Okay, if one transaction is calculating an aggregate summary function on a number of records while other transactions are updating some of other records, the aggregate function may calculate some values before they are updated and other after they are updated. Okay, suppose the initial value of A is equal to suppose 200, initial value of B is equal to 100. That means Before calculation, if I will calculate the summary of A and B, what it will be 300. That means A plus B is equal to 300. And whenever I will do some operation on A and some operation on B, after that also, if I will calculate the what a summary of both A and B, or calculate the sum of A and B, then I should get 300. But in this case, we will see. Okay. Initially sum is equal to 0, then read it will read your 200, then A is equal to A minus 100, that means A will be your 200 minus 100 means it will be your 100. Then your write A means it will 100, it will write 100 in your buffer. Then read A as it has been written 100 in your buffer, then when the second transaction read A value, first it will check in local memory no updation is there, 100 is there, that means it will read 100. Then sum is equal to sum plus a, sum is equal to 0. That means sum is equal to 0 plus 100. That means sum is equal to 100. Then read b, b value is here how much? 100. Then sum is equal to sum plus b. That means 100 plus 100, sum is equal to 200. That means here sum is equal to 200. Then read b, b value will be your 100. Then b value will be your 100 plus 100, it is 200. Then write b, b value will be your 200. Okay, that means in this case, after completion of T1 and T2 transaction in concurrent manner, A value is equal to 100, B value is equal to your 200, and sum is equal to your 200. But it is inconsistent. Okay, sum should be 300. Why it is happening? Suppose transaction T1 is updating some data items value. That means it is deducting 100 rupees from account A, and it is adding 100 rupees in account B. In between, if the sum is calculated or sum function is calculated, then generally it results in incorrect summary. Okay. Then why such transaction generally happens? One transaction is calculating an aggregate summary function on a number of records, while other transactions are updating some of these records. The aggregate function may calculate some values before they are updated, others after they are updated. This is your incorrect summary problem. Okay. And all should be avoided in concurrent execution. That means T1 and T2 should executed concurrently, but such kind of problem should not be there. Okay, that's why we are discussing. Whenever the transactions are executed in concurrent manner, such kind of problems may arise. Okay, now we are studying. Then unrepeatable read problem. Suppose T1, T2, two transactions are there, and T1 is reading some data items from the database. Again, after some time, without doing anything, suppose T1 again reading the value of that data item, then it should be same. Okay, it should be same. But when concurrent execution happens, and in between two read operation, one transaction of same data item, some updation happens on another transaction, then whenever the same read operation happens in some time interval, then it will result inconsistent value. That means it will result different value. Suppose initial value of A is equal to 200. Okay. Then first, when we will execute the read operation of transaction T1, it will read A as 200. In between, suppose T2 was executed, it will read A as 200. Then A is equal to A minus 100. That means A value will be your 100. Write A means it will update in 100 in your buffer. Then when again T1 will execute the read operation on A, then write A means this value it will read. That means 100 it will read. That means T1 transaction has not did any updation operation in between. First, it has read the data item A value as 200. Then after some time, it has read the data item A value as 100. Okay, this is your unrepeatable read problem. Okay, then why this such kind of problem arises? When transaction tries to read the value of a data item twice, when transaction T1 wants to read the data item twice, and another transaction update the same data item in between the two read operation of the first transaction. Suppose two do read operation of first transaction, another transaction T2 update that data items. As a result, the first transaction reads varied values of same data item during its execution. The first transaction reads varied value, different value. Initially, it has read 200. In second, after some time, it has read 100. Varied values of same data item during its execution, known as unrepeatable read problem. And these are the generally problems arises due to concurrent execution of transaction. Phantom tuple. Suppose in SQL some query we want to execute. Suppose this is one query to see the value of employee table, okay, the data items of employee table where salary is greater than 3000. Then after some time this transaction suppose again executed the same instruction. If in between any other transaction updated some data items into that database, then it will result in different database state, or it will result the results should be different from first. Same instruction, same query has been executed two times. That means it wants to see the database, employee database in both of the case, but in between another transaction updated something in that database, then it will create what different view of the database. That is known as phantom tuple problem. Okay, transaction T1 may read Transaction T1 may read set of rows from a table based on some condition. Now suppose that a transaction T2 insert a row that also satisfies the condition of T1. If T1 is repeated, then T1 will see a row that previously not exist called a phantom tuple. Okay, suppose initially the database state is the database consists of employee number, name, and salary. Suppose here what two rows are there which are salary is greater than 3000. One is your 1A 5000, 3C 4000. But after some time, suppose T2 transaction inserted a record 4D 3500, 4D 3500. Now greater than salary, three rows are there. Okay, when again transaction T1 execute the same query which has been executed before, then it will result this database state, and this database state and this database state is different. Okay, this is known as phantom tuple, and this tuple is known as your phantom tuple. Okay, and this generally arises due to concurrent execution of the transaction. These are the five basic problems of concurrent execution. Now we'll see log-based protocol. Till now, we have seen various problems associated with concurrent execution of transactions, and all those concurrent execution. Why the problems are arising? This is due to what concurrent access of the data items. Suppose T1 and T2 two transactions are there, and one shared data items A is there, and A is shared by T1 and T2 simultaneously. Then generally such problem arises, and such problem can be avoided if we access the data items in mutually exclusive manner. That means suppose transaction T1 is accessing some data items, then at that moment T2 transaction should not be accessed that data items. If we apply that concept, then we may avoid the concurrency problems. Okay, whatever we have seen. Okay, and this is the basic protocol. First one is a lock-based protocol, and it what generally wants to apply the mutually exclusive access of data items on various transactions. We will see that. For this purpose, when one transaction T1 wants to access a data items A, first transaction T1 will apply some lock on data item A, then it will execute its instructions, or it will do operation on A. Before applying any lock on A, or before applying any lock on A, it cannot do any operation on the data items. Okay, generally there are two kinds of locks are there. One is a shared lock or read lock, and another one is a exclusive lock or write lock. Okay, suppose two transactions T1 and T2 are there, and one instruction is there, read A. Read A, one instruction is there. Then first T1 has to apply a lock on A. And how T1 will apply a lock on A? First T1 will request a lock for concurrency control manager. Then concurrency control manager, if concurrency control manager grant a lock on A, then T1 can do the operation, read operation on A. Okay, and in this way generally this locking protocol works. We will see that locking is a procedure used to control concurrent access of data. Locks enables a multi-user database system to maintain the integrity of transactions by isolating a transaction from other executing concurrently. Understood? Okay. Locking is one of the most widely used mechanism to ensure serializability. And data items can be locked in two manners or two modes. One is a share lock or read lock. Another one is an exclusive lock or write lock. Two kinds of locks are there. Suppose one transaction T1 wants to do read operation on A. Whenever a transaction T1 wants to do read operation on A, then it requests a share lock or read lock to the concurrency control manager. And if no other locks are present, currently present by any other transaction on data items A, then concurrency control manager can grant that lock to transaction T1 so that T1 can do a read operation on A. Similarly, what is a write lock or exclusive lock? Exclusive lock, if one transaction T2 wants to do write or update some data items on A, then first it will request a write lock to the concurrency control manager. And if no other locks are present on that data items currently, then concurrency control manager will grant that lock to transaction T2. Then T2 can do a write operation on A. This is all about write lock. And how read lock is represented? Read lock is represented by lock S and write lock is represented by lock X. Suppose one transaction wants to apply read lock on data items, then how to write that? Lock underscore S on suppose data item Q. Transaction T1 wants to do that. And suppose one transaction T2 wants to apply exclusive lock or write lock on data item Q. Then what is how we will write that? Lock X on Q. Okay, these are the various instructions which are used to apply locks on various data items by various transactions. And another thing is if a transaction Ti has obtained a shared mode lock on data item Q, then Ti can only read the data item Q but cannot write on Q. Okay, suppose T1 and T2 two transactions are there and one A data item share data items in between T1 and T2 is there and T1 wants to read A, then before that first T1 will request lock S on A, and if the what concurrency control manager will see if no lock is present on A, then it can grant this lock to T1 transaction. Then after that, after getting this read lock on A, T1 transaction can read the data items. It cannot write the data items. It cannot write A is equal to A plus 5, write A. It cannot do like that. It can only read the data items of A. Okay, using this share lock or read lock. Similarly, whenever T2 transaction wants to write some value on data items A is equal to A plus 5 and write A, it wants to do, then before that it wants to apply write lock on A. That's why it will request lock X on Q, A on A to concurrency control manager. And if concurrency control manager sees that no lock is applied on A, then concurrency control manager can grant that lock. And when concurrency control manager grants that lock, after that T2 transaction can apply the lock, and after that T2 transaction can execute the write operation on A. Okay, in this way generally the share lock and exclusive lock works. Now we'll see basic rules for locking. If a transaction has a read lock on a data item, it can only read the item but cannot update its value. Okay, suppose T1 and T2, two transactions are there. Okay, suppose your read A is there. Here, suppose here read A is there and write A is there. Okay, then before reading A, and A is a common data item used by T1 and T2. Before reading A, first T1 has to request for a read lock S on A to concurrency control manager. And if no lock is applied on A, concurrency control manager will grant that lock. Then T1 transaction will lock on A, then T1 transaction can read A. It can execute this operation. But it cannot, this T1 transaction cannot write on A because it has applied read lock on A. And when one lock is applied on A, that item, suppose T1 has executing this, T1 has applied lock on A, at that moment, if T2 transaction wants to apply write lock on A, then that what request will be denied by concurrency control manager because already one lock is applied by one transaction on that data items A. That's why at that moment another transaction cannot apply lock on that. Whenever another transaction requests a lock to the concurrency control manager deny that lock. That is here. if a transaction has a read lock on that item, other transaction can obtain read locks on the same data item, but they cannot obtain any update lock on it. Similarly, if a transaction has a write lock on a data item, then it can both read and update the value of the data item. If a transaction has a write lock on data item, the other transactions cannot obtain either a read lock or a write lock on that data item. Okay, that means we can say, suppose read lock, this is your write lock, this is your read lock, this is your write lock. Suppose one transaction T1, this is your T1, this is your T2 transaction. Suppose T1 has applied read lock on a, T2 wants to apply read lock, then it can be applied. Suppose T1 has already applied write lock on a data items, X means write lock or exclusive lock, then T2 transaction wants to apply a read lock, then it cannot be possible. Okay, similarly, suppose T1 transaction applied a read lock on a data items and T2 transaction wants to apply exclusive lock, it cannot be possible. Similarly, suppose T1 transaction applied a exclusive lock on a data items and T2 transaction wants to apply exclusive lock on the data items, it cannot be possible. That means we can say whenever a transaction is applied read lock on a data items, suppose it has applied read lock on a data item A, then another transaction wants to read that data item, read lock, want to apply read lock on that data item, then it can be possible, except that all other situations will be denied. That means suppose one transaction has applied write lock, other transactions cannot apply read or write lock. If one transaction has applied read lock, other transaction cannot apply write lock. Okay, and these are executed by, these are the instructions lock a sub q. Suppose one transaction want to apply read lock on a data item, then lock s of q, and other transaction wants to apply exclusive lock on these data items, then that will be done by lock x on q. Okay, and a transaction can unlock a data item q by the unlock q instruction. That means by writing unlock q instruction, we can apply unlock of a data items. These are the basic rules for locking. Then working of locking, all transactions that need to access a data item must first acquire a read lock or write lock on data item, depending on whether it is a read only operation or not. Suppose T1, T2, two transactions are there. Suppose T1 transaction is doing a read A, write A operation on that item A. Then before that, first it has to apply a exclusive lock, because here write operation is there, read write operation is there. That's why it has to apply lock X on A. Then only it can do the operations. Okay, based on the instructions, first the T1 transactions has to apply lock on the data items. Okay, then only it can execute other instructions. If the data item for which the lock is requested is not already locked, then the transaction is granted with the requested lock immediately. If no lock is applied on a particular data items, then that can be the lock request of that transaction can be immediately granted by the concurrency control manager, CCM, concurrency control manager. Okay. If some data items, some lock is already applied on the data items, then the concurrency control manager has to analyze which kind of lock is already applied on the data item. Based on that, whether again the lock can be what given to that requested transaction or not, that will be decided by concurrency control manager. Okay, in what way? Suppose one already I have discussed, if a read lock is requested on that item that is already under a read lock, then the request will be granted. If a write lock is requested on that item that is already under a read lock, then the request will be denied. This can be explained in this diagram: read lock, write lock, read lock, write lock. Suppose on a data items, suppose T1, this is your T1 transaction, this is your T2 transaction. Suppose T1 transaction applied a read lock on a data items. If T2 transaction wants to apply read lock, then it can be allowed. If T1 transaction has allowed a exclusive lock on a data items and T2 transaction wants to apply a read a lock on that data item, that cannot be allowed. And if T1 transaction has already applied a read lock on a data item and another T2 transaction wants to apply exclusive lock, that cannot be allowed. If T1 transaction has already applied a exclusive lock on a data item and T2 transaction wants to apply exclusive lock, that cannot be allowed. This is the summary of all 4 pipelines. Okay, now we'll see, and these are the notes, these are the three important points. A concurrent schedule which is conflict serializable to a serial schedule, that means conflict serializable schedule will always get the respective logs from the concurrency control manager. Okay, if it is a conflict serializable schedule, that means serializability is present in that schedule, then concurrency control manager will always assign the logs to that schedule. But if the concurrent schedule is not conflict serializable, the requested logs will not be granted by the concurrency control manager. Okay. However, in case of incorrect summary problem, all the requested logs will be granted, resulting in incorrect value. Okay, we'll see that. Before that, this thing we will see later on. That means even if in incorrect summary problem, even if all the logs are correctly granted, but it will result in incorrect value or inconsistency database state. That is the main lacuna or main disadvantage of this basic locking protocol. That's why we need advancement of this locking protocol. Before that, we will see how the locking protocol works. Suppose this is a schedule, and here T1 and T2 are two transactions, and T1 is reading and writing data item A, then again T2 is reading and writing on data item A, then T1 is reading and writing data item B, T2 is reading and writing data item B. Then how to use what locking protocol? Before doing any operation, first T1 transaction has to request for some lock. Okay, here T1 transaction is both reading and writing on data item A. That's why it will request a which kind of lock? It will request a lock X on data item A. That means it will request for a exclusive lock for data items A to the concurrency control manager. Then concurrency control manager will grant that lock. Why? Because no other locks are present on data items A. That's why it will grant that. Then after granting, that means the lock X on A will be applied. That means lock X on A will be applied here. Then these operations will be executed. After execution of this operation, it will unlock A. It will unlock it. Then after that, suppose T2 wants to execute this instruction. That is, this is means read and write A. That means it has to request for exclusive lock. Log X to X on A to concurrency control manager. Then concurrency control manager see whether any lock is applied on A or not. Already lock is unlocked. Okay, no lock is applied on A. That's why concurrency control manager will grant that lock. When concurrency control manager will grant that lock, then T2 transaction can execute this read and write operation. Okay, then after execution of this, it will unlock. T2 transaction will unlock the locks on A. That means all locks will be unlocked. Then after that, suppose T1 wants to execute these two instructions. Then again T1 transaction will request a exclusive lock. That means lock X on B to concurrency control manager. As there is no lock previously applied on B, concurrency control manager will grant that lock, and T1 transaction will execute these two instructions. After that, it will unlock the lock on B. Unlock B. Then again T2 transaction wants to execute but read and write operation on B. Then before that, it has to send a request to a lock for this data items B, for this data item B to the concurrency control manager. That means it will request a lock X on B. This is exclusive lock because it has to read and write. Then concurrency control manager will analyze whether any lock is already applied in B or not. No, already no lock is applied on B. That's why concurrency manager, control manager will grant that lock. Then read write operation will be executed by transaction T2. Then unlock operation will be executed unlock on B. In this way, the locking protocol generally worked. Now, this is all about that what I have explained. Okay, initially T1 transactions has to execute these two instructions. That's why T1 transaction first it will request a exclusive lock, lock X on A to the concurrency control manager. As no lock is already applied on A, that's why concurrency control manager will grant that lock on A. After granting that, then T1 transaction can execute these instructions. Read A, write A. After executing of these instructions, it will execute on lock on A. Then concurrency control manager will know that no lock is applied on A. After some time, suppose T2 wants to execute these two instructions, read A and write A. Again, it will send a exclusive lock to your concurrency control manager. As no lock is applied on that item A, it will grant that lock. When concurrency control manager will grant that lock, then it will execute read and write operation. Then again after executing the operations, it will unlock the data items A. Then after some time, suppose T1 wants to execute to read B and write B, then T2 will send a exclusive lock on B to concurrency control manager. As no lock is already applied previously on that item B, that's why concurrency control manager will grant that lock. When it will grant that lock, read B, write B operation will execute it. Then it will unlock B. That will be informed to concurrency control manager. After some time, suppose T2 wants to execute read B and write B, then before that, first it will request for exclusive lock X on B to concurrency control manager. As no lock is previously applied, that means whatever lock has been applied here, all has been unlocked. That's why it will grant the lock, then read write operation will be executed, then unlock B will be executed. Okay, in this way the locking protocol works. Schedule for in this case we will see, suppose T1 and T2, this is a schedule, and here if we will apply first, it wants T1 wants to execute this instruction. What it wants to read the data item A, it will apply a read the data item A, and here it is writing the data item A. That's why it will apply exclusive lock on A. That's why it has requested for lock X on A to concurrency control manager. And as no lock is previously applied, concurrency control manager will grant that lock, then lock will be applied here. Then it will execute read A. After reading A, suppose T2 wants to execute these instructions. When T2 wants to execute this instruction, before that it has to apply a exclusive lock on A. That's why it will request for lock X on A. But already one exclusive lock is applied on A by transaction T1. That's why it cannot be granted. That means this is here, it will wait till completion of T1. T2 will wait till completion of T1. Okay. Then schedule 5, in this case, suppose T1 and T2 two transactions are there. In this case also we can apply the locking protocol in that manner. Initially T1 wants to do read and write operation on A. That's why first we have to apply a request for a exclusive lock on A to concurrency control manager, and as no lock is applied, it will grant that. Then after that, read and write operation will be performed. Then unlock A, it will unlock that. Then after that, suppose T2 wants to execute this instruction, as a read and write is there, then T2 will request exclusive lock on A. Then as no lock is applied on A, that's why concurrency control manager will grant that lock. Then read A operation will be executed. At that moment, suppose T1 transaction wants to uh, do wants to execute this instruction, and when T1 transaction wants to execute this instruction, and here read B write B is there, that's why T1 transaction request exclusive lock on B. As no lock is applied on B, then concurrency control manager will grant that lock. Then read B instruction will be executed. Then after that, as exclusive lock on A is applied, that's why write A instruction will be executed. Unlock A, it will unlock the lock on A. Then after that, no other then exclude read B and write B instructions T2 has to execute. That means T2 has to execute read B and write B. Before that, it has to request for exclusive lock on B. Then as no lock is present, is there any lock is present on B? Yes. Transaction T1 has applied exclusive lock on B. That's why when T2 wants to apply a lock on exclusive lock on B, it cannot be allowed by the concurrency control manager. Okay, then T2 will wait for the completion of T1. Okay, this is also a situation of deadlock, you can say. Okay, this is your this is an incorrect summary problem. Okay, we have already seen this example previously, incorrect summary problem. The basic locking protocol works for other schedules, but in case of incorrect summary problem, all the locks will be granted correctly, but the incorrect summary problem will arises when such kind of schedules are there. The inconsistency of data item will be there. Even if all the locks are granted properly, all the locks are applied correctly, but it will result such kind of situations cannot be prevented by this basic locking protocol. Okay, we'll see that. Suppose T1 and T2, T1 transaction is sending or transferring 100 rupees from account A to account B, and T2 is the summary of we have to display the summary of account A and B. Okay, but before all the updation, that means here we are deducting 100 rupees from transaction A, here we are adding 100 rupees on transaction B. Before all the updation of transaction T1 performed, in between the T2 transaction is calculating the summary of transaction A and transaction B. That's why it was creating problem in case of concurrent execution. And this problem, whether this problem can be solved by locking protocol or not, we will see that. In this case, we will apply to execute these instructions. Suppose T1 transaction wants to execute these three instructions. To execute this instruction, before that we have to request for lock on A, exclusive lock on A. As no lock is applied on A, that's why concurrency control manager will grant that. Then all the instructions will executed. Similarly, all other instructions will get executed. You will analyze it at your home. Then you will see all the locks will be granted properly. Here also the lock read lock is requested, and that has been granted. Here also read lock on B is requested, that has been granted. Your exclusive lock on B is requested, that has been granted. That means all the locks has been granted correctly. Still it will create inconsistent data items or inconsistent database state. Okay, that's why though the concurrency control manager will not face any problem in granting the locks in this case, the above schedule gives incorrect result of transaction T2. Okay, that means this is the problem which cannot be avoided by basic locking protocol. And to solve the previous discussed problem, different alternative solutions are possible. And one solution can be by delaying the unlocking process. That means the unlocking is delayed to end of the transaction. Unfortunately, this type of locking can lead to an desirable situation. Just see here. Suppose in previously we are transferring 100 rupees from account A to account B. Then these three instructions, read A is equal to A minus 100, write A. Before that we were applying exclusive lock on A, and we were granting, concurrency control manager were granting that lock, and after that we were unlocking at that place. But what we will do, suppose we will not unlock the unlock on A here, we will delay that process. Suppose, then what result we will get? If we will delay that process, then deadlock will happen. We will see that in this slide. Okay, suppose first we want to execute these three instructions, read A is equal to A minus 100 and write A. Then T1 transaction will request a exclusive lock on A. It has requested exclusive lock on A, and then concurrency control manager grant that, then it has executed these three instructions. But here we will not unlock on A, that way we will delay. And when we will delay, then T2 transaction has to execute these instructions, read A operation. Then to execute this read A operation, before that we should apply read lock on A, and when it will request a read lock on A to concurrency control manager, already exclusive lock is applied on A by transaction T1, then concurrency control manager cannot grant a read lock on A data items. T1 is holding an exclusive lock on A, and T2 is requesting a shared lock on A. The concurrency control manager will not grant the lock permission to T2. Thus, T2 is waiting for T1 to unlock A. Okay. Similarly, another transaction T3 is there, and T3 wants to apply a lock. But T3 transaction is transferring 100 rupees from account B to account A, suppose. Then again, in T3 transaction also, it wants the exclusive lock on B. Then after some time, it wants the exclusive lock on A. This also, here also the T3 transaction depends on T1 transaction. That means in this case, T2 transaction depends on T1 transaction. Again here T3 transaction depends on T1 transaction. And such kind of situations are known as your deadlock situations. T2 is waiting for T3. T2 is waiting for T3 to unlock B. Similarly, T3 is waiting for T2 to unlock A. Thus, this is a situation where neither of these transactions can ever proceed with its normal execution. This type of situation is called deadlock. If we do not use locking, or if we unlock that item as soon as possible after reading or writing them, we may get inconsistent state. On the other hand, if we do not unlock a data item before requesting a lock on other data item, deadlock may arise. That means the basic locking protocol cannot solve the problem of data inconsistency and deadlock. That means even if we will use this basic locking protocol, data inconsistency, sometimes we are getting data inconsistency, sometimes we are getting deadlock. That means incorrect summary problem cannot be solved by this basic locking protocol, and sometimes deadlock is happening. Okay, that's why to solve these two problems, we have to do some updation, or we have to do some enhancement on basic locking protocol. And this is all about the locking protocol, this locking protocol. And it tells you that suppose T1 transaction has applied a exclusive lock on A, lock X on A. Suppose T1 transaction has applied a read lock on A, and T2 transactions wants to apply a exclusive lock on A, then that cannot be granted. Then suppose at that time T3 transactions wants to apply a read lock on A, then that can be granted. Suppose after some time T4 transaction wants to apply a read lock on A, then that can be granted. That means in this case, one read lock is already applied by transaction T1. At that moment, suppose another transaction T2 wants to apply exclusive lock, that cannot be applied. But at that moment, suppose T3 transaction want to apply read lock on A, then that can be applied. T4 transaction wants to apply a read lock on A, then that can be applied. In this case, T2 transaction will wait for a longer period of time. This is known as starvation. This problem is known as starvation problem. Okay, and the summary is that the basic locking protocol, that means whatever we have seen, it solves many data inconsistency problem, but in some situation it arises data inconsistency. Basically, the incorrect summary problem was not solved by this protocol. And second one is your sometimes it creates your deadlock, and in some situation it arises starvation. These are the three problems which cannot be solved by basic locking protocol. That's why some enhancement is needed on that basic locking protocol. That we will see in next class. Thank you.